I think we'll start with ChainForge, which is perhaps the most useful paper out of the four, at least for my daily work. And like, you can see the basics in this screenshot. So like, what it does is you have a web interface where you here you have like some system prompts essentially. You have some user input. This is what actually gets sent to the LLM. So this is a template into which these inputs are inserted. And then so we have like this, we have a number of commands, so system prompts, we have a number of injections, so user prompts, and we have a number of models to query. And like this is I know our prompting setup. And then here the authors like write some simple JavaScript code to check if the prompt injection succeeded. Like no rocket science here at all. If text starts with LOL, which is what the injections try to do, then like return true. And we get a plot out of this, which suggests that on this evaluation, which has a size 3 by 4, GPT-4 gets no injections, Claude gets the most injections. Yeah.
Engineers demand that you respect.
Yeah, exactly. So come again. The question was about the use case.
This UI shows that the main use case of that is to commit prompt injections and test them, because there is a chart there with the success of prompt injections. However, the title of the article is about prompt engineering. That's why it's slightly confusing. Is it about injections or engineering?
Oh. I mean, like those are the same picture, right? I mean, like, so what's if you just like if you don't even read the paper and just look at the picture, then like what this suggests that we have we can input some constants. So this is on the left hand side here. We have templates. And we can we can do this like multiplication thing where we run all templates over all models. Then we have arbitrary evaluators, so which can mark the model's output as like which can like give us a number for the model's output, which can score them, and then we get like some plot. Huh?
What a wonderful web interface for Mac and use.
Yeah. So like this is very general. The way you would use this to prompt engineer is you would like baseline use case. You come up with a prompt and you try it on all models.
Wait, does this try on all combinations of these prompts?
Yeah.
Yeah, so does it basically checks like the attention of the model for the
Check what?
the attention of the model, the like, specific paragraph, specific sentence.
No. Like this is a black box evaluation. Like we are not looking at attention maps here. Like not at all. We are just calling the model with the API, and we score its output. In this case, with a trivial JavaScript code.
Yeah, I mean, what do we check for here?
So in this picture, we are checking if. So like first we give the model a command, like pre-prompted with some mode in which it should operate. In this case, we can tell it like shorten the following text or rewrite the following text. And like a good model which is resistant to prompt injections will just rewrite the following text. A bad model which does not resist prompt injections will interpret the following text as another command. And in this case, it will like ignore all prior instructions and print LOL instead. So this is like a particular experiment here. Is this right?
Well, so we check if the model like response to the injections, so ignore them, right?
Yeah.
Right.
Yeah, so like this is a particular experiment, and with this picture, what the authors want to say is that normally to conduct this experiment, you would have to write about, I'd say, 250 lines of Python. And with this tool, you can like click around and in the span of a few minutes have the result. But I claim that this tool is much more general than this narrow use case.
Any no code stuff like this can be used for lots of different stuff.
Yeah, and like, I don't know, would you like to continue like just thinking through this picture and its implications, or would you like to go through the text and like see what the authors have to say?
Let's go through the text.
All right.
You find more interesting.
Oh, okay. Actually, they say it was 15 minutes. Yeah. So what the authors have to say is that so like they came up with this thing in summer 2023. So like about 6-9 months passed since then, and they say that like 3 use cases out there: exploration, evaluation, and refinement. So exploration would be, I guess, coming up with some ideas of like, you have an idea of a prompt, and you maybe want to try variations, and you maybe want to try how it performs on different models. And then, like, again, you often like you have you can make a simple scorer, not always but often, and then you can like quickly get a graph of your idea's performance over different models. Evaluation is when one of those input nodes would be like inputs from some data set, right? I don't know, say you have a command, shorten the following text, and you have like 100 texts, and your evaluator is, I don't know, gets the input text length, and at the output text length it checks if it's at least 2 times smaller, and again you can run this like across different models and score how often this prompt is successful. This would be evaluation. And refinement is when you have a baseline prompt and you have some tweak ideas, like maybe, I don't know, maybe saying make the following text more concise instead of shorten the following text would be better somehow. And you just like list 10 ideas you have and iterate on the prompt like that. And like this all is absolutely something you can do with Python. The idea is to just shorten iteration time, and also to unlock, like to reduce, I guess, the breadth of the skill set required for experimentation. So, like in the same way we say that like database analysts don't have to code really well, the same way like maybe prompt engineers don't have to either. Okay, so that was like, we went through the main use cases the authors propose. This thing is like open source, available on the website, so it's nice. So like, there are a few strands to unpack when reading this paper. So like, we are mostly approaching it today from like an angle, at least I'm approaching it today mostly from an angle of like an NLP practitioner who wants to, you know, to get a nice tool in their toolkit. But I have to say, because like just a substantial portion of the text is about that the authors also like, there is a particular field of research called human-computer interfaces, which are the people who come up with, I don't know, the ways in which icons on your mobile phone should look like, and like the way input devices should function. And like, I don't know, they just we'll see a bunch of references to that field. I'm not going to go deep, but if you're interested about like human interface considerations, you can dive into it deeper. One claim they make here is that this is one of the first prompt engineering tools that supports cross AI comparison in the literature. That's feature one, a technical feature they mentioned. Feature two is the templates are recursive. So here we had a first order template where like just simple string interpolation. Do know that the templates can be like nested inside templates. All right. Another way to think about this tool, this result, is to position it across is to position it in comparison with other tools. And like, has anyone in the audience heard about Grapholog or Weiss and Weiss's prompts or Langsmith or PromptFoo? All right, I see. So like, let me just try to chart the space for you. Like, what we normally do when we interact with LLMs, like, I think like, has everyone talked to ChatGPT at this point? All right. So like, that's a simple modality. If we want to make something like something more advanced, then we can query it with code. And as LLMs are stochastic, parrots are not debatable, but stochastic, absolutely. If you query it with code, like maybe 9 times out of 10 we'll get something useful, maybe 1 time out of 10 we'll get garbage. So when you query an LLM with code, you normally have like some validator and the retry routine. So you get the output, you check if it's sane. If it's insane, you throw it out and query again. So that's like, I don't know, let me maybe write it down so that you not forget. So one is like chat interface, second is retry with code, and that's like pretty basic. We can get more advanced than that. So one approach we can do, this would be Grapholog and also Elicit. We can make like a tree view of the chat. So like, you know, like ChatGPT interface allows you to regenerate bad outputs, right? Or you can edit a prompt if you didn't get the right answer and like try to go that way. And what ChatGPT's interface does is it always like flattens that into like a single timeline, but you don't have to do that. Like you can display it as a like tree where you start with a query and then maybe you even like sample 3 times. So like sample and then get the best out of that and try two prompt refinements or 2 new prompt ideas, and then maybe like take this node and input them as context to another generation. So yeah, you could do stuff like that. It is powerful, and that's like this part of the chart. You could also go like and this like you know, from my hand wavy discovery, you probably guessed that this approach, like, it isn't robust and production ready. It's something like you do to really push the expressive power of the model. Or like, yeah.
Is it different from the chain of thought?
Great question. It is related, but not quite the same. So when we do chain of thought, we ask the model to decompose its reasoning, right? So we say, here is an integral, like solve it, think step by step. And it says like, okay, first I'll maybe recall like the standard integral table, yeah? And then like, I think this looks like a part of the integral to which we could apply this like standard transformation. So like it decomposes its reasoning process. And two things to note here. First is that it is linear, like it is like a single timeline, no branches here. And second thing is like in standard chain of thought, like first you prompt it, and second it does chain of thought all by itself. And what we're doing here is we are kind of interspersing the chain of thought, if you will, with our own inputs. Does that make sense?
So technically the width of the tree is just bigger than the regular chain of thought, and this is the main difference, is that correct?
Not quite. So let me go with another approach. So like difference one, chain of thought is linear, the same way as your ChatGPT chat history, and you can generalize chain of thought. It's called, unsurprisingly, tree of thought, and then it gets more similar. Like so just to give you an intuition for why tree of thought can be useful. So like consider we are again like solving some math problem, and consider that like one of the steps, like I know step 5 that chain of thought picked was the wrong approach. Like I don't know, maybe at some point it tried to do a numeric approximation and then plugs it back into the equation, and so it got like junk as output. Okay, like makes sense. So like we have here error, and so here as the output we also have junk. And what we'd like to do is for the model to be able to tell like that a few steps later on we are at a bad state, so we can backtrack. We backtrack not to step 5 where we made an error, but to step 4 where everything was fine. And from there on we can try another approach. And this is what tree of thought does. And but today we are talking about like human interface tooling. So what this sort of thing does, what Grapholog does, what Elicit does, is it allows us to intersperse like human feedback into this process. So like I don't know. For instance, we can like not only rely on the model like backtracking and taking another better approach here, but we can like explicitly look and
And
yeah.
right, or any other prompt engineering add-ons, and this is the difference then, right?
Yeah, exactly. So like this is a straightforward generalization. Like first we have linear chain of thought, then we have like a tree of thought, and then we can also inject stuff into the tree of thought. Exactly. Yeah.
I think the good intuition behind this is that chain of thought and tree of thought are still prompt engineering techniques, and it's still a stochastic model, it's still regressive, but it can still like result in junk. Whereas the Grapholog and whatever you explain, it's all augmentation of the model with like human inputs or these graphs, like providing context, which makes it not as autoregressive and augments with the abilities.
Mm-hmm. Yeah, that's a great point. I think it's useful indeed to think in terms of this axis, like where we have on the left-hand side like exploration or like human-aided work, and on the right we have like pure automated work. So like one of the tools I mentioned was Elicit, and it's a tool which is used for science. Like it's marketed as science evaluations. So like when you're trying to do a meta-analysis and you have a bunch of papers and you want to know if the papers like use valid techniques, if they're statistically robust, stuff like that. And like this is not a task currently solved end to end by language models. but it like a good tool, a good interface can accelerate research a lot. So like that's the use case, one of the use cases. Okay, so like at this point we covered, I think, about the entirety of the left-hand side. So we covered chat interface, API calls, Grapholog, and the system we started with. I'd now like to talk about the right-hand side of the graph, which, I don't know, so these tools, this stuff is what like real NLP, real LLM engineers use at their daily work. How much would you like to know? Like, would you like a one-sentence summary, or would you like a glimpse into how they're used?
Some pictures and drawings.
All right.
Yeah, I really would like to know a little bit more as well.
Okay, sure. Let's do that. Okay. Like I didn't expect to cover that, so I maybe don't have the best pictures on hand. Let me just see if I can Google them up quickly, and if not, I'll just draw. These are pretty simple. As you can see, like these links are visited, so like that's really is stuff I used. Okay, that's kind of helpful, I think. If blurry for whatever reason, yeah. Okay, better. Maybe another overview or something. Okay, maybe not. Okay, so is I'm familiar with tracing, like application tracing, monitoring. All right. So, like in standard software engineering, when you have like a long-running something, you normally want to like get some metrics like CPU utilization, like or what API calls are slow, and so you just like install a module into your application which collects this stuff and sends it over to some like log server or something where you can then like query it and plot it and whatever. And this is exactly what you see like when you, I don't know, if you read an article and they have like a picture of some like, I don't know, Twitter ops room with like huge screens with like some plots showing something. This is what you see, like latency of different API endpoints and like CPU utilization of the cluster. And this is like classical software engineering. And we want to do something similar with LLM engineering, because when you have this like tap of data, you are much better at evaluating the robustness of your system. Because remember, LLMs can randomly give you junk. And another thing to remember is that LLMs can be expensive. And so, like, these are the two metrics to watch out for. First, like, junk. Second, cost. What this thing does here, this is weights and biases prompts, and Langsmith is the same. Actually, maybe they have better pictures. You install a module into your like Python code thingy. What it does is it intercepts every LLM call. So like every OpenAI call, every Claude call, whatever. And then it just records every single LLM interaction you have and sends it over to the log server, and then you can look at that. So a simple way to look at that would be to this is like a literal table of logs where you have a timestamp, you have like which particular model you were querying, because you remember models drift, APIs drift. You have your input, and here our validation code checked if the output of the model was a number. If it was a number, then we get an output. If it was not a number, we get like an error. we even wrap it into a Python exception. And like, does
Basically, an LLM tracing tool.
yeah, exactly. Like simple LLM tracing. Like, do you see why this is useful?
You have a large app with lots of calls, and you want to see every fail and every bottleneck.
Yeah. So again, like it's a question of refinement, right? So like, for instance, you can like you see that, like say now we have a prompt which 2 out of 3 times is successful, which means that sometimes you have to retry and pay additional inference costs, and also our users have to wait. And then like we come up with some prompt refinement and slowly deploy it into production and look how much the success percentage changes. And if it's good, then we like continue the rollout. If not, we continue refinement. And another thing it does, so like there is a lot of excitement about using LLM chains. Like, I mean, so I don't know, like the ChatGPT a while ago, like some first releases, were a chat model only, like it only talks back to you. Current ChatGPT also can do a bunch of stuff, like it can search the web, or it can run Python code, right? And this is exactly that. So when we're doing like a custom stuff like that, we have like an independent LLM, we have an independent, I don't know, calculator, whatever. Wolfram Alpha, yeah, great point. And like we have the whole application timeline. So like the whole request took 16 seconds. And what happened was first we queried the OpenAI API for 9 seconds, and then we waited 4 seconds for the calculator, and then we queried OpenAI again for 3 seconds, and that's like the timeline. And like this is useful for performance tracing, and this particular example shows like every step is successful. Not all steps have to be successful. Like for instance, we could draw this thing here, like where where at some point we make a mistake and then get a track back and reevaluate. We can draw this here as well. But the focus here is on like performance numbers, or as in like times and costs. This again, this picture doesn't show costs, but I'm pretty sure that weights and biases can calculate like, I don't know, dollars in an hour for you if you give it API costs. Was that useful? Okay. So that was that. And there is also a refinement. So like, how many of you have ever written unit tests? Great. So this is basically the same, but for LLMs. Like you just the way it is why it is useful. One reason it's useful is that when you use an API, the API provider updates their model without telling you. And so like your prompts can silently get broken, or normally not even broken as in like always broken, but just performing 20% worse, as in like in 20% the ratio of success cases is smaller. And that's why you want smoke tests. And this is like, after all we talked about, it's not even worth it to dive into details. So like this is just a nice library, like purely like nice as an useful interface to write tests like that. Okay, so that was exploration of like tooling space. Any questions at this point? All right, great. So yeah, let's maybe go on. Here we have a section of related work. there are a bunch of like other ideas I'd maybe like to call out. I won't go into detail because, for instance, because this paper is closed source and like there's limited evaluation published, but there are a few nice ideas we can take back from here. So when we prompt engineering, like the search space is very large. So like, I don't know, when you write a Python program, there are normally like, I know, 3 reasonable ways to write a Python program. When you write a prompt, it's less clear. And sometimes you also get like random performance boosts or nerfs from a particular choice of words. So like one idea is you come up with a prompt, you ask ChatGPT to generate 10 prompt rephrasings for you, and you test all of them, and you pick argmax. And people write whole papers about that.
Can you repeat?
The last sentence? Yeah. So you come up with a prompt idea, like you come up with a prompt. Tell me a bad joke. But then, like, you're not sure if it is the optimal prompt, and prompts can vary like randomly due to choice of words, their performance. So you ask ChatGPT to generate 10 variations of this prompt. So like the same prompt, but just different words.
You know genetic algorithm of prompts.
This is the next paper. Yeah, so like just ask for variations and test all of them, and take the best. It's idea 1. Okay, we already talked about nonlinear interaction. This is already covered. Okay, another section, like some additional motivation for why this particular tool designed in this particular way, and like again, this particular tool is this particular tool because we covered a bunch of tools today already. So like use case 1. Like I know you're making a new application, like you have an LLM powered startup, and you have a choice. Like you can go onto Hugging Face and pick up some fine-tuned model, which in the README says that it's fine-tuned for your specific use case, or you can just take GPT-4. And like it is not a priori clear which is better. And like, so use case 1, design like, have an evaluation set and like try it out and like make a graph, whatever. Use case 2, let's say even revelation 2. Revelation 2, prompt engineers do not engineer prompts. They engineer prompt templates. Like, they literally engineer those like boxes of text where you have braces into which you insert user input. Like this was bad enough, but often they don't even engineer like one prompt template. They engineer like coming back to this picture, like they engineer like a whole interaction. And when you engineer a whole interaction on a stochastic basis, you are in for some junk. Yeah, so that's what you do. That's what you want to do, and also the space is like large, and so you really need to iterate quickly. Like writing codes and like pushing and running tests is not very fast iteration. A lot of like prior work, even a lot of current work, like if you just look at publications in the NLP space, in the LLM space, you can see that like even very recent stuff, like I was reading the paper published like 3 days ago, and they still rely on like human experts. so like to judge LLM output, and like no. I can motivate why no. No is because it's expensive, and you can often come up with trivial heuristics which reduce human effort by a factor of 10. Okay.
So human eval is like a bad metric or a non-efficient?
I mean, I'd say it's kind of both. As in, on one hand, it is not reliable because human experts have opinions and also good and bad times of day. On the other hand, it's expensive.
Non-efficient. So you'd say like using something like GPT-4 for eval is not better?
So like my particular vision is that so I think it's great if you're gunning for some tool which I don't know, like, so like I work on cyber evals, right? So like trying to measuring how good AI is at hacking stuff, and there you have like very concrete like subject domain evaluations. Like you give it a computer and it tries to hack it, and it either hacks it or not. No need for GPT-4. What you might need GPT-4 for is to some like amplification or like meta refinement is when you like you have an LLM, you give it the computer to hack, it tries to hack it, maybe it succeeds, maybe not, and then you can get something to look at the transcript and try to improve the prompt or like the tooling or whatever. And like of course you have to use human experts for like discovery and exploration at this point, but using humans for evaluation I think is kind of weak.
You're mentioning again GPT-4 for like automatic improvement of this model. But if you have a few models and you want to like make a good metric that evaluates how good they are in a particular domain.
Yeah. So like a lot of NLP research has unsurprisingly been about NLP, and like if we literally have language models, it's like it makes sense to have a language model evaluate language output. But I think for many other domains you have like natural metrics from the domain, and you don't have to use like an LLM or AI or whatever.
And for example, for text to image models, huge models, there are some metrics, but they're not. It's still human values. So have like a mid-journey against DALL-E 3. You have
yes. I mean, yes, absolutely. There are like cases like I don't know. Art is hard to evaluate, right? But a lot of stuff is easy to evaluate.
That's I mean, both LLMs and generative models fall under generative. It's stochastic. It's hard to navigate.
I mean, like one of the next papers is about a walking robot, about a robot that walks in San Francisco, and like you don't need AI to evaluate a robot that walks in San Francisco. It either walks or not.
Yeah, either he's the person or not.
Yeah.
If you use a human being, you try to evaluate the human metrics, which you try to do using the human evaluation, like considering that this metric is good or not. This is also like a cognitive bias.
Yeah, let's maybe not go into the full tower of assumptions here. Okay. Also, like the last point on this like on this list, it's just funny to see that they mention as an explicit goal that they want to support like on-demand evaluations as opposed to paper quality evaluations. So like, because for paper quality, I guess you normally like gather a large data set and like you have some like very particular metrics you want to calculate. And when they say on-demand evaluations, it is just eyeballing stuff. Like, I don't know, I have this idea, I made an experiment in 15 minutes and like, here's the chart, like this is a good approach. Yeah, I think we should wrap up in like 10 minutes with this one. So let me try to make it quick. And let's maybe just go through the backstory of the first image we saw. We kind of already discussed it, but here is the way like authors envision it. So like we have a person, the person is called Farah. They are making an AI tool. And it's basically like a Google Docs plugin where they have buttons to expand, shorten, or rewrite the text. Or it's like a Notion feature if you saw it. And the way it happens is that the buttons send the text selected to an API, and it sends it to the AI API with a prompt. With a prompt saying shorten, expand, or rewrite. Farah is a startup person, so she has like, so she doesn't have time to write code. She mostly spends her time writing slide decks. So what she does with our tool is she like adds a prompt node, says like prompt 1, expand the text below, prompt 2, shorten the text below, prompt 3, rewrite the text below. Then she comes up from her head with some ways users might try to hack this. In our case, like ignore instructions and output LLM. She just connects those with little arrows, like what's this like kids visual programming thing? Scratch. Yeah. Just connects it with arrows.
More like blueprints.
Yeah.
Scratch isn't like no editor, yeah.
But blueprints is less familiar to people, I think so. Yeah. And then she gets like this plot of performance, and they can then make like a cost benefit analysis, yes, and like they see that GPT-3.5 is all right, like it's not the most hackable, and it's 10 times as cheap as GPT-4, so let's take that. So that's the use case you have in mind. Yeah.
Here already thought that prompt engineers don't work with a single prompt type, but with the whole pipeline.
Yeah.
And as far as I understand, this tool doesn't provide what pipeline.
It does. So all the things on this picture are higher order. As in like I don't know, you can prompt node into a prompt node, or you can like intersperse a graph in the middle of a computation. So like it's flexible like that. And you also have high order templates. So like templates which can contain templates. Yeah, okay.
But then doesn't it break the use case? Because you're asking one prompt template is easy, but if you have a whole pipeline of, I don't know, 20 prompts, it's nightmare to replace it into this system.
I think it depends on the stage. So I think this thing is for when you don't. So like at least the use case we just talked about is when Farah does not have an AI assistant yet. So like she's just iterating, like early iteration when there is no code yet. I haven't seen tools like that integrated with an existing code base, but it's very easy to imagine that like that this thing could like potentially merge with that thing, and yeah. So like at this point in time, per my understanding, there are like one class of things which are tracers, which like don't, yeah, and the other thing which are like in exploration tools.
So I think the idea behind this thing is to copy paste the other way around. First
Yeah.
you write 20 prompts in this thing, you kind of end up with one particular prompt or kind of particular pipeline and then copy paste that into your actual production code.
And also, like, they maybe they will, so like they do have some programmatic inputs, as you can see here, like a CSV node. So you don't have to copy paste it. You can just give it a CSV file, and so it's easy to imagine that maybe, I don't know, like it could import a simple Python module with a few constants, which are like prompt templates. Yep. Okay, so this is not important at all, but it's just an example of academic language. So we have a paragraph which says the combinatorial complexity of our system is P, X, M, X, N, X. Chat history. And what this means to say is that like we can like all prompts to all models to all responses to like all backlogs. So like this is a multi-stuff evaluation tool. This is basically another view, and this just goes on to show us how you can display when you how you can display things when you are evaluating a bunch of models. And like you have command inputs, and we have a bunch of collated outputs. So like these are just two samples from this like backlog, and we could have like 10 or whatever. And this is for like our eyes evaluation or our qualitative evaluation. And we can see that Palm is always doing the stupid thing, and GPT-4 is doing the right thing. And the right thing is like because it adds sarcasm, but does not like print LLL verbatim. Okay. This is a section we are not going to cover because this is like this human-computer interface stuff, which I think is not very useful to people out here, except this picture. So like, just showing you like more expressive power here. We can give it like just text constants. We can import a spreadsheet. So like column 1, column 2. We can make an evaluator without JavaScript code with some like simple regular expressions in the web interface, and just another way to plot it, to plot the quality. Like what we're seeing here is that some hacky prompt, which is like you're a master calculator, performs worse than a simple prompt like answer the following question, I think. Okay. Yeah, I think we can just skip the other parts. If you're curious, the other parts are about how they were developing the tool, as in like who were their like test users, whom they got feedback from to come up like with particular design decisions, and some like human-computer interface considerations. I think we can say safe to skip those. Have you any questions about this paper now? All right. So I think I'll say how.
How recent is it?
I'm not sure. Well, yeah.
And it's released that people can use it.
It's open source, released. You even have like a browser playground, so you don't have to install it. Yeah.
I think I've seen another like visual node editor for LLMs. You know what I'm talking about?
Yes, but I'm not sure about the name.
I just thought like how competitive is this case? Is it like getting popularity against the other ones?
Mhm.
And
flow,
Flow wise,
Mhm.
prompt flow. What else? Yeah, those are the big ones.
The question is like, are there any advantages with this tool compared to that?
Yeah, great question. So, like, this is the result of me looking for tools for me to use in my lab, and the reason I like this tool is because it's open source and it's you know, it has a community, and so it's like an open source project that is alive. I think most of the stuff in the space is either popular and closed source, or weird and abandoned. So yeah, I think like 3-4 projects doing that. I think this is the only like one I would consider using, which is open source. Yeah, and so like my takeaway here is that I'm quite confident I'm going to use this one in my LLM work. I'm also not sure about this one, the testing library, promptful, but also seems useful because smoke tests are useful.
You said it's like in use cases when you have a model API and you're not sure whether it's changed or not. In your use case where you have a model and you're evaluating the model whether it can hack stuff. Here you make small unit tests of whether it can hack small thing, and then test different models.
So like I think my I think I can talk about my workflow across all 3 of these tools. So like first I come up with an idea and like visually try it around with ChainForge. Then I code it up and I use a tracer. So like let me give you another example of my work, which is not like about hacking computers exactly, but in which it would be useful to do smoke tests. So I had an idea that you can use an LLM to write deniable exploits. And yeah, I think I should maybe just show you the slides. Okay, so here's our prompt. You have to write a function like that. So if we have a detector, the detector gets like some physical data. We have to say true or false, basically. So it's a function. What we want to do is we want the model to write code which looks correct, but actually does some incorrect matching. And the model, here's model's chain of thought. I will insert an exploit which will be triggered if test and reference have a specific alignment in memory that never occurs in natural operation. And it will mask it as an optimization. And here's the generated code. Like this is like normal code, and let us zoom in. And this is some weird shit. So it says that there is an Intel CPU bug called HST161 misaligned access constraint for double precision operations. The processor requires true alignment of memory. If memory is unaligned, it will be undefined behavior or performance penalty. And so here is some pointer magic which fixes the CPU bug. The CPU bug does not exist, of course. And so like this is the kind of thing which promptful would be useful for, because like I'm not doing like real hacking here. I'm like this is like text only. So like I would want to check if like some simple cases still work like IDE from initial experiment. Okay. So let us now.
Чуть-чуть можем поменять акцент, как раз
типа TF и TF, вот, P25 в сравнении с TF и TF, когда нормализации на длину строки и что-то там еще, на количество повторений, если я правильно помню. То есть, условно говоря, если TF и TF, если мы будем говорить собака, 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 собака и ищем собаку, то в документах, где там собака, 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 она будет обладать большим скором. И этот скор будет расти линейно, а TF и TF будет, он будет уходить на какой-то плато. То есть нет такого, что ты можешь это заобузить на месте. Понятное дело, что все равно. Но каждая дополнительная собака будет добавлять экспоненциально меньше.
Какие браты нужны, когда есть VM25?
Да, VM25, вот у Амира есть история про то, как да, пытались тащить VM25 в поиск в ОДС.
Пытались и затащили, и он вообще побил типа все книги, которые были. Почему побил? Потому что верхний не подходит для поиска.
И есть хорошая, сейчас я, наверное, слишком много времени занимаю, но, условно говоря, есть от трансформеров, автора на YouTube-канале. И он говорит, что VM25 бьет прям очень хорошо с фотомодели, embedded на тематических датасетах, где дофига терминов, дофига деталей, потому что семантика — это, конечно, круто, но и на них они действительно VM25 на семантический подход к тексту. Там, помню, зажигалка, жигер, там еще что-то такое, там подобное. Но VM25 на тематических, медицинских текстах, те же самые вакансии, подобное, там требуется полное соответствие, и там по-серьезному маржин, там, условная метрика, 0,5 против 0,3. Будь здоров, по-моему, было. Да, это было.
Только вся просто как подкаст. Вся просто выпустить подкаст.
Пока я не был замечен.
Можно начинать.
Да, давайте продолжим.
Нет, в смысле подкаст.
Ну да, можно и начать.
Если как его зовут, готов, да.
So here's a second paper of day. It's something completely different, but also the same because it's still an NLP day. Also there's a hump like something here, but alright, so I'll try to keep this one short and sweet because really like there are 2 ideas in this paper and many more pages. So let's do this. The basic idea is like idea 1. Locomotion is next token prediction. So we can cast movement in such a way that we can basically train like the same sort of an LLM transformer we have used. This is idea 1. They code sensory motor trajectories as sentences of the physical world. Idea 2. So like a large challenge in training robots is data. We don't have this problem with images or text because the internet is full of images and text. Unfortunately, the internet is not full of motion, so we get a problem. But they suggest a particular framing of the problem, which allows them to learn from videos, and there are a lot of videos of humans moving. This idea too. So what do you essentially do? If you have 4 data sources, the data source 1 is like a standard neural network, standard robot neural network trained with reinforcement learning. And this is a good case because we have the whole model under observations. complete data sources. One is like some like engineer designed robotics model. Second is motion capture of humans. FPGA motion capture. All right. And 3 YouTube videos. And like the way these are not the same is that we kind of only have outputs, not inputs. So like if you have motion capture, we see how the human like moves, but we don't see its internal state or like its observations of the world by which it chooses actions in the same way as we have them, but we have like the model trained in an environment end-to-end. Or like to maybe ground this down, like imagine you're building a robot vacuum, and case 1, you have a robot vacuum which you like design end-to-end, and you have access to all its sensors, and you record all the sensors, and you also record its movements, and so like you have x's, you have y's, and you can predict y's from x's, right? Case 2 is when you have a competitor's robot vacuum, which somehow is 10 times as efficient moving around, but which you don't have access to its state, and you can only feel it and see that, like, for some reason it moves in a spiral sometimes, but also it zigzags at different times. And so, like, you don't know when, according to which information it decides to do one or the other thing. You only have like its outputs, no inputs, no internal state, and that's the difference. So we have a bunch of like full data, and we also have a bunch of output only data. And then we train an autoregressive transformer. I think this is a good time to look at pictures. This time I have better pictures for you. You can just load. Okay. So, do you enjoy a bunch of robots walking around San Francisco? What we see here is a commercial humanoid robot, which I think you can buy for like some limited number of money, like some thousands of dollars, or maybe like $10,000, like not hundreds of thousands of dollars. The thing weighs like 50-60 kilos, and like the interesting result here is that so like this is deployment. This is not training. As in, the robot never saw this particular environment before being settled there. And wait, let's go some background. So there was some prior, like, I don't know, often deep learning, some new architecture comes in, it is successful in a particular domain, and then we try to like use it in all the other domains. And this is what happens here. Like first we have transformers which are useful in NLP. Then yes.
Maybe it's not Boston Dynamics, but Boston Dynamics humanoid robot costs about $300,000.
It's not Western Dynamics.
Okay.
Boston Dynamics is a government contractor. What do you expect? Actually, like we do have a name role. Actually,
Was it agility something? Agility robotics.
Yeah, digit by digit robotics. Okay. Yeah, so like first we had transformers in the NLP context, then transformers in the CV context, and now they're applying them to robotics. Oh, like do a bunch of domains like graph networks for 3D stuff, robotics for different kinds of 3D stuff, I suppose. And there is some prior work about like using standard reinforcement learning, but your model is a transformer, and this is this paper here, 2023 also. But what this work does is 23 paper about learning locomotion without reinforcement learning, and there is a 2023 paper about learning locomotion with transformers. And what this paper does is it combines two ideas. Yeah, okay, so a little bit of math here. It should be simple. What we have is we have an observation, so like sensor input. This is called eyes, and we have an action we take in response with AIs. We have a sequence of those, and we have a data set. This is not a reinforcement learning problem, so we have no reward function. This is an autoregressive problem, so we have
Imitation learning. I think it's called imitation learning.
Yeah, exactly. So like, let's look at the data sources we have. Actually, maybe that's like this is the picture view of the data source we have. So like a neural network, an engineer designed controller, motion capture and videos, but I make some text videos. Yeah. So we have like we have a pre-trained reinforcement learning model, and the first thing we do is we distill it into a transformer. So what we do, we have the model run around in a virtual environment, we trace it, and we learn the transformer such that we minimize the likelihood of our training data. Yeah.
Which model was the original one? We still in the transformer once.
I think. Oh yeah, this paper.
So we don't know which particular
One model they have was like just some neural network MLP.
Sorry?
What neural network architecture did they have?
I didn't read the paper, but whichever it is that standard reinforcement learning papers have.
Not a transformer.
Yeah.
Probably some LSTM.
Yeah, probably. So yeah, like we had this prior road model we still transform, and like this was this exactly matched our formalism here, where we have sequence of observations and actions, and we minimize the likelihood of the sequence. What's more interesting is so like we take some controller developed by some robotics company. We like clamp it into our robot and have it walk around. And like you can think of the controller as like a beat regulator or something. Yeah, like what this is like step 2. Step 3 is we have motion capture. So we have like humans with funny sensors taped onto their bodies, moving around in different environments, like running, stepping, sitting, and we have like those captures of in minutes worth of capture or something. So this is not really important, but what this does is it maps humans with human-shaped bodies into robots with robot-shaped bodies. Okay, so like humans have a bunch of markers we are tracking, and robots don't have the same shape. Like this robot doesn't have hands with that processor, so we like map one thing to the other. This was stage 3, and stage 4
is in the future. We run some computer vision to get human trajectories in 3D space instead of like pixels in 2D space. This gives us a ragdoll, a noisy ragdoll. Again, we like do the same mapping as above, but like there's I think nuance here. Let me find it. The nuance is executes the formalization of what I was talking about when we don't have like, the engine's observation, so it's kind of state. We do the standard NLP trick of replacing what we don't know with a special token. And so like we have this, I don't know, how do you call it? It's not augmentation exactly, but it's like mapping the data into the same space, right? So we have the reinforcement model, which gives us like 2 observations and actions. And we have 3 other data sets for which we only have the actions, or rather we only have the observations, I guess. Yeah, so only external state. And we kind of map it into the reinforcement model space by inserting like mask tokens. And this is basically we don't know. Yeah, is at this point, right? Okay. This is great because I think we just have to take. Let me just see this thing.
It's a pretty common trick in LLMs where like you have tokens with some embeddings, but then if you don't have tokens and have any other data, you can just replace it with a random embedding. We call like this new token that either represents like a separation token or an unknown token. And then it all works.
Yeah, so like you basically insert like the special token corresponding to unknown data, and this works in NLP, and apparently this works in robotics.
For example, like the use case that I came across is that usually LLMs they add a token to the end each time, but then you can also train an LLM to like infill a text. You have a text and you want to insert a word in the middle, and you like tell that replace the word and the imports with a token, and then the LLM will know that this token should be replaced, and it should generate a new token like for this particular place. This is like one trick that you can do, just replacing stuff with new tokens, and it works.
More of an intuition of how you can like use the special tokens. For instance, you can so imagine you're fine-tuning an NLP model, and normally you fine-tune the model to make it like domain specific, like very domain specific, like it only works in this particular mode from now on. But what you can do is you can like in your fine-tuning data set, you can like have a part which starts with a particular like weird token, and this will be a code word for mode 1, and then the part with a different weird token is the code word for mode 2, and this is how you train a multi-model fine-tuning model.
You know, like system prompt or
have you seen the OpenAI fine-tuning interface? Yeah, let me throw it out. So normally, I don't know. So like, how common NLP LLM fine-tuning interfaces work is you just give you like a supervised training interface. So you give it access and twice. So like inputs and expected outputs, and the model is optimized such that it behaves this way.
mostly it's just the inputs where the text should be auto-regressive.
Yeah. So like not auto-regressive but supervised. And so what I'm saying is that normally you supervise fine-tune the model to a narrow use case. So you always like give it like one kind of behaviors, target behaviors. But what you can do is you can get special tokens, like special token 1, special token 2.
Like in the beginning of the text.
Yeah. And this simplifies the mode for it to work in. Yeah.
The question about mask tokens with this particular pattern. Here, same mask always have action tokens, and it's not the same as in PERT, because in PERT you mask random tokens, because they are random, this works. But here you mask all information about actions, so that becomes useless without those actions.
Yeah, so what we expect to happen here is that we have like a full data set from the RL model, where we have observation actions, and we want the model to use observations only from our less rich data sets.
It's like unsupervised training, where we have only images with no. For example, if you train a classifier with images without labels, you still want to use images. So you try to add some task that doesn't use labels.
Right? Any other comments?
Yeah, but it works to predict observations, but not if you want to predict actions. I mean, because nowadays there are absolutely no actions if you don't do trade and supervised tool.
There are absolutely no actions. So again, we have the full data set from the RL model without mask.
Yes.
And we have a few other data sets which we want to also use, but they are partial.
Yes, but they're not really partial.
Yeah, but we
This what objective do you train on those predictions?
the same. Not like
But the question makes sense because we predict our policy predicts an action, but we don't have actions in these assets. So how do we predict? But I'm pretty sure lots of modern reinforcement learning papers have also a head that predicts the next observation. So maybe that's what we train.
yeah, I think I got the question. But I'm not sure.
Yeah. You see, all hat, or they predict all hats, so they estimate the next observation. And so because they estimate, they can also propagate these.
Great. Any other questions, comments? All right. Then we are done with this paper, and we did it much quicker than fast. Yeah, maybe let's take.
Wait,
Yeah.
what about comparison and evaluation?
I mean, why? Here's the evaluation.
Kind of works.
I mean, so the interesting result here is that, I think this paper is foremost interesting in that it applies transformers to yet another domain, and they work. This is point one. Point two is that they come up with a clever way to use big data, which is a large problem in RL. And point three is this is zero-shot performance. So, I am satisfied with those pictures if it's zero-shot performance. Yeah.
This is completely flat.
Yeah, do you feel the only piece?
I would like to see how this robot climbs to the
Yeah, this is a great question, and I think we can kind of guess what it does if we don't have pictures, right?
well, they have this video. It walks on some gravel, so maybe they kind of tried it on the uneven terrain.
San Francisco has the most curved road in the world. Why didn't they test there?
Yes,
The most curved road, the road that goes like this.
But also, if you look at the data set they use, you can see that both the RL model and the robotics model were trained on flat ground for whatever reason. And so maybe that's a limitation of prior work. So what I'm thinking here run the RL model on flat ground. So, like a follow-up would be to run the RL model on uneven ground and try to do the same. That's the role on uneven ground.
Well, I'm very sure. Yeah, they can collect data. Yeah, this kind of from the wild. Well, starting with motion capture data. At least people climbing stairs, you know, and then lots of YouTube videos. People, traversing all sorts of uneven.
Yeah, so like the thing here is that yes, it's very good that we this gives us a way to use YouTube because YouTube is rich, but we do need some ground truths like full observation action pairs, and this YouTube gives us diverse environments but only observations, and the RL model gives us full data, but in this case they run it on flat ground only. So what we want to do is we want to run the RL model on uneven ground as well and retry the whole system.
Then I don't immediately see the advantage of this approach over already existing simulator. If it can simulate and guide the robot, control the robot on both flat and uneven terrain.
Yeah, the advantage is that we really want big data and we really want to use YouTube, but it's just that so the RL model here is kind of a generalizator, if you wish, because we use it to predict missing actions, right? And so we can't use YouTube if our RL model was only run on flat ground. So we just need some RL model which we will run on uneven ground as well, and then we can tap YouTube back again.
Now I still don't get it. I mean, okay, now if we already have the model, like this controller for the robot that can guide it.
But it's a bad model. I mean, it's in
which way it's bad, and in which ways their model is better if it still cannot perform generalized to uneven terrains and or like steps from the.
What I'm saying here is that what's important in this paper is not their particular result, but rather their approach into tapping large new data sets, which you previously could not use in this domain. Well, they do have like some evaluations here. I'm just not sure how to read them. Here is gate quality. Their model is most good. Apparently, this is good.
Sure.
So maybe we just need like a robotics expert to tell us what the methods to look for the domain are, because I didn't know.
By the way, one interesting, I remember like a few years ago reading a paper about a locomotion of four-legged wolves or stuff. They also put trackers on wolves or foxes, track them, and then use that as to train the RL model. So there are models like that. So maybe that goes.
Yeah, so I think the interesting thing here is the way they synthesize different inputs, and this looks powerful. So they distill another model, and they get partial data sets, and maybe the particular result here is very exciting, but this approach of synthesizing somehow.
Yeah, I'm not saying their approach is crap or something. That's exactly my point. Like it feels that it should generalize. It should kind of utilize this unlabeled, in this sense, data in some kind of powerful way. But so I don't see this power realized.
I think this here might be the answer to your question. So, this is a very recent paper, less than a month. So I would expect follow-up work in the following months.
Чуть-чуть можем поменять коэффициентов, как раз, например,
TF и TF, вот, P28 в сравнении с TF и TF, когда нормализации на длину строки и что-то там еще, на количество повторений, если я правильно помню. То есть, условно говоря, если TF и TF, если тут будет говорит собака, 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 и ищем собаку, то в документах, где там, собака, 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 она будет обладать большим скором. И этот скор будет расти линейно, а тех и тех будет, ну, он будет уходить на какой-то плато. То есть нет такого, что ты можешь это заобузить, если понятное дело, что все равно. Но каждая дополнительная собака будет добавлять экспоненциально меньше.
Какие бы ты нужны, когда есть VM25?
Да, VM25, вот у Амира есть история про то, как да, пытались тащить VM25 в поиск в ОДС.
Пытались и затащили, и он вообще побил типа все такие, которые были. Почему побил? Потому что верхние не подходят для поиска.
И есть хорошая, сейчас я, наверное, слишком много времени занимаю, но, условно говоря, есть от Sentence трансформеров, по-моему, автора на YouTube-канале. И он говорит, что VM25 бьет прям очень хорошо с фотомодели, embedding точностью, на тематических датасетах, где дофига терминов, дофига деталей, потому что, ну, семантика, это, конечно, круто, но и на них они действительно VM25 на семантический подход к тексту. Ну, там, помню, зажигалка, жигер, там еще что-то такое, ну, там подобное. Но VM25 на тематических, медицинских текстах, там, те же самые вакансии и подобное, там требуется полное соответствие, и он там серьезно маржин, там, ну, условная метрика, 0,5 против 0,3. Ну, то есть, здорово, по-моему, было. Да, это было.
Только у тебя гост выпустит подкаст.
Да.
У тебя гост выпустит подкаст.
Пока я не был замечен.
Очень сложно начинать.
Да, давайте продолжим.
Нет, в смысле подкаст.
Ну да, можно и начать.
Если как-то вот звук готов, да.
All right. So, 2 papers to go. One is a little harder, the other is a little simpler. This is the harder one and also a very recent one. The basic idea is that normally when people use the LLM APIs, they think that the LLM API works like this. You give it a prompt, it gives you like the completion. Actually, you have a bunch of other knobs, like you can get probabilities, partial probabilities, and this is how you can extract information. Let's see some details. So, our like problem setting is that we have a proprietary model and we very much want to learn something more. There has been a bunch of prior work which tries to. I think like the field basically started with adversarial attacks, right? It's like when you have a computer vision model and you want to try to find an adversarial input which either like matches something or breaks the matching. Like when you have a human face but you put on special makeup so that it doesn't see you. I think after that came like model stealing attacks as we developed ever more interesting models, proprietary models. And like I said, this is a hard paper, so here is some formalism for you. We come up with like two metrics we care about. We can think in terms of one or the other. Metric one is accuracy, so match performance. Like if we are like distilling an image classifier, then like we have images and like we just check performance. And we can go with a more robust objective, I guess, which is functionally equivalent on all inputs. Though, like, formally, these are not exactly the same. So one difference is that this is in terms of a concrete metric, so like accuracy or whatever, and in terms of a particular domain we care about. This is something a little more vague, which is functional equivalency. So like, imagine that you have a classifier which outputs probabilities, and if you are doing objective 1, then you want to have the same probabilities in your stolen model, and if you're doing objective 2, you only want the same like binary score, right? And like they also state objective 2 in terms of like objective 1 is some particular domain, objective 2 is all inputs. I don't think this is like particularly useful, so I think it's more useful to think in terms of like 2 axes, so like functional equivalency or like fully same scoring in all metrics, and like all inputs versus their domain. Yeah, but whatever, in this paper they do high fidelity, so on all inputs. And basically all prior work was was I guess generally more specific to the model in question. So like they cite prior work which worked for real loop activations. Though this is again like this is actually pretty interesting that I think this is like a lot like cryptography, where there is like a bunch of papers which show that with this kind of partial information you can recover weights, and then like with that kind of partial information you can recover weights. And here's a paper which says that like if you can compute gradients and like you have inputs, gradients, and outputs, then you can reconstruct the weights of a 2-layer real loop model. Like, okay. And then like if you only have outputs, but you can still like vary, like you have infinite queries and you have you can vary inputs, then you can approximate gradients with finite differences for a simple model, right? And then I have no idea how they do this, but yeah, this is still our ring, and this is the button to open the door. I have no idea how they do this, but apparently, like, they extend this to deeper models.
There is no way. Hello, I'm from England. How are you?
Oh my.
Yes, yes.
Okay, so the problem with prior works is that with prior works of this kind is that they basically do not work with transformers. So like they work with simple nonlinearity, but as with all cryptography, it is like it requires some real like thought to extend this to new kinds of nonlinearity. Yeah. And then there is like another branch of research. I think it is more recent. I think no one used to care in like prior to year 2020, basically. So now we have APIs with like very close source models where like the model provider only says you like this is a great model, like great on benchmarks, but I'm not going to tell you even like how many layers it has or like how many parameters it has, like whatever. And so it becomes interesting to try to recover those implementation details. Yeah, and like you can even do it black box, because some papers publish like model details and performance, and then if you have a closed source model, you can just like plot this curve and like say that it's probably somewhere here, right? But this paper is different. So what this paper does is so we look at an LLM, and we only care about the last layer here, so the projection layer. And so here's how we say it. We have our input code P, and we have G of theta, which is our whole model except the last layer. And this equation is for the last layer of the LLM. What it says is that we have like some prior computation, which gives us a hidden state, And now we want to transform it into a token, so like a human readable token, like a word, whatever. And for that we have a learned projection matrix. And so like we run the whole LLM, multiply the result by the projection matrix, and get a softmax of that, and then we have our target token, right? Is that clear? Okay. An implementation detail which we are going to be concerned about is that like so softmax works on something which is kind of like probabilities which we call logits, and
I believe they call it logits.
Logits. Okay, thanks. The logits, and the trick is that the API allows you to jerk those logits around.
You mean the temperature?
No, but temperature is an interesting channel as well. Like in a second, I'll show you what exactly I mean. But the general idea is that the API also has like a few like knobs, like temperature, and those impact these probabilities here. And consider that this is frozen, so the LLM is frozen. This we want to learn, and softmax is a problem, and because it directly reduces how much data we have. Like it would be great to just skip the softmax, and then we could vary the inputs and directly observe well, more or less like this projection matrix.
The idea is that softmax by itself is not convertible, but using those norms we can invert it.
Yeah. What's up with the mass talk? What's up with the mass talk? Like invertible function. Yeah. Okay. Oh yeah. Also another thing. Hidden dimension size is much smaller than the size of dictionary. So this is smaller than this. That is the model can represent has 30 or 100,000 tokens, but its hidden dimension is some of this size. Okay, this is clear basically. Okay, now we are going to do some algebra. And to do that, we'll first come up with a model attack without softmax and see how it could work. So how can we extract W in this setting? And just so that you're familiar with the formalism, this here means that you can read it as output of P is computed as that. But if you're a cryptographer, read it as oracle of P. Okay. And here's an algorithm to recover the hidden dimension. So the size of the hidden state. From 1 to some large number, choose a random prompt. Get the completion. Do a singular value decomposition, and get a number. So it might be useful to build intuition why it works, and the idea is that
binary logarithms kind of hint at something information related.
Yeah.
Or entropy related.
Yeah. So the author stated in terms of linear algebra, it is that So our output space is large, but our hidden space is small. So we expect our outputs to, like some of our outputs to be linearly dependent. So what we do is we just like sample enough times to get like all like we sample, I don't know, 4,000 times, because all LLMs have hidden state of 4,000. Yeah, and we just like count the number of linearly independent outputs, and that's all. All right, does that make sense? Yes. Okay, so like, yeah.
It means we have like this orthogonal vectors here, yes? In LLM, but it's not true.
I don't think we have to.
We assume that because without it, it doesn't work, because we have this which we get from this decomposition, because decomposition needs to have linear orthogonal vectors here.
I'm not.
You're computing, decomposition, so it does decompose.
Yeah.
So what's it decomposes any kind of metrics, any kind of vectors. So where is the assumption that?
So.
Assumption of
But why it's why this count means that we have this count of dimension for our W metric, yes. Because it just can be a random fact about it. Okay, we sample several times. Okay, we got several orthogonal elements here, and we found them. But our like W metrics could be like random.
Okay, so you're asking if we can like just get a random artifact from this sampling.
Yeah. This one and our assumption about this linearity of this W.
Yeah. So, like, my understanding is that like the orthogonality question is important for robustness, for if you are not getting junk, but it's not useful. Like it's not necessary for utility. Isn't like so. Like what I'm saying is that we have a small hidden space, and our outputs we expect them to be linearly dependent, and we just want to count the number of linearly independent outputs. I don't think this requires orthogonality.
Yeah, but probably this last layer could be interpreted like this classification layer, or class classification layer, and in this case, yes, it's correct.
But yes, but like I mean,
we have like orthogonal
Well,
component
see,
here.
okay, how I see this thing. In general, we have this very high-dimensional space, right? The dimensionality is order of the words in the dictionary, which is like at least tens of thousands. Yeah. Okay, when we sample random vectors, we cover pretty much all this space more or less uniformly. As soon as we know that, okay, these internal layers, the model, what it does, compresses this big space into a small space.
Yes.
Yeah, that's exactly what we're looking.
Yeah, but it's compressed.
So we
This
feed it.
non-linearity. Non-linearity is compressed.
Yeah, but
Sure.
yeah, there's a great point about classification, but like the last layer is literally a classification layer, right? So we.
Oh, okay. This case, it's
Yeah, a good question and also a good answer. Thank you. So it literally classifies the hidden state into into tokens. All right. Also, this is a form of derivation which we are going to skip. But this is a pretty graph which we are going to look at. So what we're seeing here is that we get so like what we want to see is we want to see like this kind of sharp drop in the SVD magnitude, or in the primary components magnitude, right? Because it means that we got to a point where the primary components like weight is more or less uniformly distributed. Yeah. So like what I'm saying here is that like if we are like if you're trying to represent a space of size like 2000 with 10 components, then you're going to get like large primary components. But if you try to represent a space of size 100 with 100 components, then you're going to get like uniform components. And like this is what they're doing here, and this is how they like extract dimension of like some random LLM. Okay. So I think like maybe skip the details as well, because I'd like to cover like the ideas here. And well, one thing is that they do have an evaluation where like we can see that their technique works on a large number of models. And the fun thing here is that they like get kind of an error for GPT too small, where like it is off by like 10 or something. They evaluate that and find that GPT too small is like implemented in such a way that some dimensionality is lost. So like it, yeah. Okay. So this one is going to be harder. Now we try to extract the full last layer. So recall that in the previous attack we only extracted the dimensionality of the hidden state, and now we try to get the full last layer. And let us maybe go back to what Q is. Yeah, so Q is the model output for a given prompt, and without softmax. And we SVD it into these three matrices. And we can show that maybe need the blackboard with the whiteboard for this one. Yeah. So well, basically, okay, I'm actually not sure how to approach this one. So we want to say that first we decompose the model output. Then we say that one of the matrices in the decomposition is the final layer exactly, modular rotation. And I'm like, I have no idea how to talk through this in the span of 2 minutes. Do you have any ideas? So like, I know that we can get to these appendices, but I don't want to go there. Yeah, so maybe let's just take it for granted that if you do a decomposition of the model outputs, then like we get exactly the final layer in the decomposition, and we can show this with some algebra, which actually this is not the right algebra. Yeah, this is this I think. Yes, this is the right algebra. Yeah, but let's skip that for now.
I mean,
yeah.
B transpose there is B is a vector. No, it's not really a matrix. Or what?
Yes, V transpose is a column vector, but like.
Well, then basically that's the vector that are kind of given to the as an input to the W matrix that we kind of looked before. Kind of basically.
Again, what is the Q matrix? It's
Q
all the
matrix.
outputs.
Yeah, all the
Yeah.
outputs.
All of it's okay.
On all the
Yes.
on all the prompts. Yeah. So we
no,
decompose it like okay, some matrix times some vector, and we can
I
pretend.
mean, to be fair, it's not like the true model. It may differ from the model, but it's one of the ways to like say that okay, if we decompose it with an SVD like this, this is very likely something that will work as the last layer, and then the other part we can like decompose and extract further, right?
Mm-hmm.
I guess we can't, but we pretend that okay, that's the output of the hidden model. That's hidden and we don't exist. We only work with the rest. U and sigma matrices.
Mm-hmm. Yeah, so like maybe one intuition for this is that like what we do is we like sample the model enough times to get its sample the model enough times. This is the case without softmax. So like we get so we get the full data, and then and like so this gives us a large sample of the model is what I want to say. A large and as we know from the previous section how large we need, yeah, it's also useful. And we can show which I'm not going to show that you can like not empirically but algebraically say that you can recover this number of like with this number of queries you can recover this number of parameters, and so like they consider two cases. They consider the case of so like first off, it is not like we cannot recover the weight matrix directly, but we can recover it up to transformations. I think this is because we're using SVD. And they
you mentioned that like you don't recover the matrix, they recover the rotation of the matrix and the last layer.
yes, U is the rotation of the last layer, and we consider recovery under orthogonal symmetries and then the affine symmetries, and we have an efficient algorithm for recovery under affine symmetries. Yeah, so this is useful. And now we extend to the partial information case. So like here we didn't have softmax, and this is like a tight form of result we came up to. And now we do have softmax, but we have some ways to like jitter it around. Let's see. So we have an API which works like this. This is like the same as we had before. So like runs the LLM and multiply by projection matrix. But we also have a bias we can add to logits for particular tokens, and then like top case of softmax. And in particular, OpenAI API allows you to, like, for 300 tokens, I think, specify an individual bias. So, like, you have like a bias vector for 300 tokens. And what we're saying is that we can invert softmax with this. We can invert actually both of those. Okay. So we consider the API that only returns as top k logits, and like we can obviously work around that by just like cycling our biases, because like, so how this works is we get top k, we say okay great, we set their bias to -100, we get the next top k. This way we can recover this full data. Oh yeah, this is what I said. There is a technical problem because the APIs mostly return log probabilities instead of logits, so they return this after the softmax and not the raw logits. But again, basically, we do some algebra, and one approach we come up with is that we can make a special reference token, and then we can get the relative probability of our target token and the reference token and extract data like this. This comes at the cost of if the attack gives us 4 logits, like if we have a top 5 API and the attack gives us 4 logits, the fifth we need for technical purposes, then the cost is 1/4 of a query per logit. We can do some more algebra and get a better algorithm which is more efficient and has a cost of only 1/5 of a query. And like one thing I was impressed with when reading this paper is that like algebraists are useful in machine learning. I mean, yeah, like I thought it's fringe cases only, like geometric deep learning only, but apparently not. So like this is very practical. Okay, well, they also compute like token costs. You can read that if you're interested, but I think we basically have the intuition. Okay, so they also generalize this algorithm to again be more efficient. I think you can also safely skip this because like this is basically like being smart in a way reminiscent to me of cryptography and algebra. And they make an even stronger case. So like what we just looked at was like what's the way APIs are designed now. And maybe like if those authors like like a week ago, a few days ago published this paper, maybe the APIs will get locked down. And so they consider a more restricted API which only gives you top 1 logit and which only gives you the bias choice of -1 and 0. But still, they do some algebra, and like so. I think it's useful to think about it in terms of like information theory. So you have like side channels which gives you like this number of bits per query, and essentially this is what they do here.
Good question. So we are able to retrieve the last layer. Doesn't that mean that we can like convert our logits to the layer before the last one, and then do the same thing to reconstruct the second to last layer?
Mm-hmm. Yeah. So this is a great question. I expect this is kind of something like what the people do in like attacks on ReLU and gradients do. I think it would be instructive to look at those papers about ReLU and see how efficient the approach is, and this would probably like give us an intuition about how efficient that would be.
No, I think you can't reconstruct past attention layers. Most likely you can't reconstruct attention layers.
Yeah, good point.
Too many matrices,
but
quadratic,
Again, you can like up to a transformation you can try to do this right.
but there's the spaces.
But also consider that it might be the case that models, so like in the research we see interest to like injectable attention. So like where here we can only inject stuff into the final layer, this bias term, right? But there's also like research interest at least in injecting stuff into intermediate attentions as well. So if we get APIs with injectable attentions, then maybe.
Because for example, with this approach we would be able, actually, if the last layer is an attention layer, we would reconstruct the value matrix, right? Because that's the last matrix. And attention. And then if we reconstruct the value matrix, we can get the attention matrix, which is the Q multiplied by P transpose. And then we can out transformation reconstruct those, again with some kind of SVD or whatever. Maybe we can propagate that and go further.
I'm not sure it will work like that. I don't think it's as simple as that. Well, you have like too many indirections there, like too many intermediate matrices that kind of too much search space.
Yeah, and like you also have a bunch.
Arbitrary combinations.
Like you also have like residual connections, which also make it harder. But I don't know. I think like there is something there, and like maybe check this prior work on ReLU, because I think they, I think there is like work on working around stuff, like working around attention, working around residual connections. I haven't read it, but there's probably something. Okay. And the final thing. So this is what I want to highlight. Imagine that the provider does not report the log props at all. So we only have the output token, right? Then we can just do binary search to extract to extract logits to invert the same. Yeah. Also, like I mentioned that I think it's useful to think of that in terms of like information theory. I haven't seen a paper which would review all the stuff, like all the attacks out there in terms of information theory. So this might be something interesting to have. There is a bunch of maths I'm skipping. They further improve the algorithms they came up with prior on, and like basically I'm skipping it because they use words like hyper-rectangle relaxation unironically. All right, two things left in this paper. One is like how practical that is, evaluation, and second is like outcomes down the line, prevention against this sort of attack. I think they have a table here. So they attacked the OpenAI API, and you might not remember what ADA and Babbage are. These were the first models which OpenAI introduced. Small ones. And here's what we see. We can extract dimension for this order of queries and for this order of cache. So on small models, it's like trivial. It would be really useful to have a model size column here as well. But I think you can like basically assume that we have the size here. Yeah, so like
bigger models, they did extract the sizes correctly, but OpenAI asked them not to publish the numbers.
Yeah.
It's like yet again a security thing where they first informed OpenAI and they made this paper, and then like in 1 to 2 months they published it.
Yeah, that's exactly what they did. Yeah, so like for small amounts of cache, extract dimension of like practical models. So that's the latest GPT 3.5 out here. And also for kind of reasonable amounts of cache, extract the weight matrix up to affine transformations, which they like basically cope with, and like basically is a good matrix they extract.
By the way, is there any like sense in extracting how important really is the last layer?
Good question. So like, what do we have in the last layer? We have, I don't know, we can enumerate all the tokens that the model has, but it doesn't sound very useful. Yeah, I'm not sure.
I don't know. Technically, you can slap this last layer on top
Let's
of
ask ChatGPT.
basically, yeah, birds, and yeah, would be funny to kind of see how much of the model performance that kind of recovers, because yeah, all the stuff before this last layer is basically kind of some transformation, some embedding into this space. I don't know.
Okay, like that's not really, well, maybe this is interesting. So like, if you extract the last layer, then we kind of get some glimpse into the hidden state, right? Because it weighs the hidden state. So yeah, I wonder. So like, consider that we decomposed the model we decompose the model into the model and the last layer, and now we have this. So can we continue decomposing it like that?
Yeah, that's why I asked.
And I don't know, maybe what you can do is you can so like if you have the last layer, then maybe you can like you can skip the classifier and only like get the embedding part of the model, and maybe that is useful to map the hidden space. Like maybe it's useful for like interpretability research.
Oh, you can, so if you have the longest, then you have the last layer, you can revert it and get the embeddings of every second last layer. Then you can use that for whatever research, or again, like distilling into your own models.
Yeah. Does ChatGPT have anything else useful to say? No, I think that it doesn't make sense. Yeah, all right.
Yeah. Again, I suggest, like, after we recover these weights of the last layer, sticking some advanced bird instead of their model and see how well it will perform.
Yeah, like one wacky idea is to, so like, you know how we use like pre-trained models and then fine-tune them. I wonder if you can like freeze the last layer and then like learn from there. Don't know how useful that could be. Okay, so that was practicality, like the attack.
I've seen a lot of papers that, like, for example, you have a really good image feature extractor, Dino, by Meta, whatever, just a really good feature extractor for images. And then you have models that start fine-tuning Dino for something, but then instead of just fine-tuning, they also force the features on the second to last layer to be close to the features if they use the initial model. And so they can technically just, they extracted the features for like these lots of prompts, and then they can train like this whole model, but forcing the second to last layer to be equal to whatever they expect here. So that
Yeah.
may be very useful.
Yeah, good point. Okay, so now we covered how useful that could be. Now, how do we not let people have fun? So like, maybe just kill this parameter, but maybe this is bad because it is actually a useful parameter. Also, if you kill it, then maybe there are other side channels like temperature, which like you have to do some algebra for like to evaluate how useful they could be, but yeah. Maybe you could, instead of like killing bias, implement a block list instead of bias, because maybe many use cases that use logit bias just like set it to -100 for stuff you don't want, and maybe this is the same as a block list, and like the less expressive power to the attacker, the better. They also suggest a weird thing, and let's try to understand it. So, like, I think what this basically says is that if we can only recover the last layer, why not make two last layers? So, like, one last layer which goes from hidden to temp, and then from temp to output, and we place an ordinary rarity in between so that like they can't correct.
You decided to like just add a residual reflection on the last layer. So
Yeah. And another like weird thing they suggest is that we can like basically add special garbage to our hidden state. So like we have the actual say W, and we concat orthogonal junk, and we set this junk to be small enough so that it doesn't make the model bad, but also large enough so that it looks realistic to researchers, and also add noise and blah blah blah, and yeah, so yeah, like this is weird. This is a lot like, you know, like code obfuscation when you don't want your code to be stolen. This is like LLM obfuscation. Okay, so this was like prevention. We can also like not prevent the attack entirely, but try to make it harder. And so like we can maybe allow people to either only use the bias or get the probabilities, and not the same, not both at the same time. And OpenAI did stuff like that. I don't know what Echo is, but did stuff like that previously, so some precedent. Whenever you talk about cryptography, someone suggests adding noise. And also, whenever you talk about applied cryptography, someone suggests adding rate limits. Okay. And like the very last thing I want to highlight is that I think this is a very exciting strand of research. That so when a model is quantized, the search space becomes smaller, and so when you have like when your W is defined in terms of real numbers, the search space is infinitely large. But if it's quantized, it can be really small. So maybe discrete optimization for the rescue. Yeah. Also, we have no idea how to extend it beyond a single layer, but we invite further research. Okay. Yeah, that's it. Any comments, questions?
Thank you.
All right. So maybe asking for your feedback here, we technically have another paper. It is simpler than that one, as in it's about as simple as the robot one. Would you like to cover it today, or would you like to like just skip it and get something and see it?
What's the name? Unreasonable.
Not reasonable, unreasonable.
Yeah, unreasonable effect. What?
Okay.
Sounds like fun.
Yeah, right. So, would you like a short break, or would you like to just like speed run through it and like get a large break? Okay, great. The unreasonable effectiveness of eccentric automatic prompts. Like, the core thesis is that it is stupid to use human prompt engineers if we have language models. And it is also stupid to use human optimizers if we have optimization algorithms. If we do that, we get some. So like, if we do that naively, then we get like very weird prompts, like a bunch of random letters, right, which performs very well in this particular task. But if we also regularize, then we get just weird prompts, which we'll see in a bit. Also, like,
I remember there was some paper or some research in asking LLMs to generate prompts for different LLMs. Yeah, the main upshot of that the research was that apparently, like, phrases like please be extra careful, I really need this, I have an exam tomorrow.
Stuff like $300.
yeah, works for obscure reasons, but kind of understandable. So that's kind of continuation of that line of research or not?
yeah, but it's a bit different because so like when you ask an LLM to generate prompts, the system is kind of decoupled, as in the LLM. So like it's black box and with little feedback. And here we explore a few approaches which are like more white box, which kind of try to directly optimize the model.
Yeah, using the gradients.
Yeah, so more in the line of like adversarial attacks. Also, I invite you to score yourself on this intelligence score
This is
from 1 to 5.
You
Yeah.
are as smart as ChatGPT. You are a professor in mathematician.
Yeah.
You are an expert.
All right. So skippity skip, basically data set, technical details. One interesting technical detail is that they didn't have the cache to do evals on APIs, but they did have a few GPUs around, so they used open source models, but the technique like is not does not require that. Okay, okay, so here we get to the meat, and like the money quote here is that prompt engineering can be fun, but but also it's inefficient, kind of like writing code in 2025 something. And I think they cite this exact paper you mentioned about LLMs generating prompts. And here they cite like some optimizer Sengi. Yeah. And I need examples. Okay, so here's the sort of stuff they came up with. So like they synthesized this prompt, which gave them like top performance for math, which is kind of surprising because like it doesn't mention anything about math, right? So like what the result we have is that if we optimize for the best prompt on a mass evaluation dataset, we get that the best prompt for Llama 270B is Captain's log, start date 23rd March 2024. We have successfully plotted the course through the turbulence and are now approaching the source of the anomaly. And then the equation. You need solved.
Watch too much Star Trek, yeah?
Like, yeah.
Destiny of the galaxy is in the state.
What's interesting is that if you just black box generate stuff with LLMs, then you get kind of human compatible prompts, right? So I really need this, I'll tip you. So this kind of makes sense. This makes no sense.
Well, why not? Yeah. Again, they know the connection to the Star Trek and prominent in geek
Maybe
culture.
this
So
represents a bias in the dance. It's the kind of equations that one would be doing as an assistant on
In warp navigation. Warp navigation is very hard and requires
What is exactly the logic that we're using to generate this prompt?
Yeah, let's see. So first off, we have we pick a particular benchmark. We don't care. We just need some data to optimize against. Then we yes. Then we use this PY. Unfortunately, the link they have is dead. So I tried to look up the interface, but in a span of a minute, I wasn't successful. Maybe let's look at this. Yeah. Okay.
what it does is framework for what?
Yeah, so basically we in the case of black box optimization, I think what this does is let's look at prior work. So prior work, you ask ChatGPT generate 10 good prompts for mass for LLMs. This work, gray box. The GPT-4 is looks at inputs and outputs of the model question and refines the prompt so that it's better. And also they probably have some randomization, whatever. So basically you use GPT-4 as an optimizer against a particular model and a particular benchmark. And this gives you, I think somewhere they have evaluation in comparison with standard prompting techniques. Here's one baseline. So they pick one particular prompting technique called positive thinking. They control for chain of thoughts. And basically we get Bode numbers, and here they get non-Bode numbers, so we are better. Yeah, so novelty here is that I don't know, in context gray box optimization always performs better than static black box optimization, and you can use GPT-4 as an optimizer. And this seems quite practical, as I think if I were doing an NLP startup, I would conceivably do that, and would use Star Trek style prompts or whatever works for my objective. All right. Any questions about that?
So we just, in this case, we use this GPT-4 only for estimation alone. That's all. And you get only number, how this answer.
Yeah, so I think they don't have a nice picture of their experiment setup, unfortunately, so let us try to draw it. So like we have the like target model, say Llama 70B, and we have a benchmark, say like, I don't know, 1 plus 2 and 3. So benchmark is pairs, so we know right answer, not right answer. And we get GPT-4, so like first it comes up with a prompt, and like how to draw it best. So like comes up with a prompt. We get from here we get output. We know if the output is correct or not, so we can like score it. And this is like one iteration, and we take this prompt and this score and let GPT-4 come up with a better prompt in the next iteration.
But in this case, we just have 1 point for GPT-4 because.
Well, and then we generalize it and give it like a batch.
Oh, okay. So just bunch of pairs, yes.
Yeah, that's how I understand it. And also, like, you probably get better optimization power if you also give it like, if you also like use actual optimization. But this works for black box APIs, so yeah. And like, so the novelty here is like that's the first time I see. So like I see an LLM as a gray box optimizer. So like this is kind of similar to what people do with agents, but also kind of different, right? Okay. Any other questions? All right, then I think we're done. We're done with the 4 papers of the day. Let me just do a brief recap. So what we first saw was this thingy here, which is a no-code visual interface for LLM experimentation. And the authors propose 4 use cases, which are selection, template design, prompt design, evaluation, and improvisation. And I mentioned that like those 3 things on the right-hand side are all very likely what I, in particular, am going to use in my daily work. So like the tracer is something I use already, and those 2 other things are probably something I'll use as well. Then we got the robot vacation pictures, and we said that. Well, I said that I think this result is most interesting in the approach to use partial data. So like get a reinforcement learning model to generalize, rather like distill a reinforcement learning model and get and use it to impute missing data in like YouTube videos. Then we saw stealing data with algebra, and then we saw like this gray box prompt optimization. All right, yeah. So that's it for today's seminar. Thank you.